Welcome to another data science deep dive on our technical track. In the following presentation, we have Colin, Waldman, Senior Machine Learning Engineer at One Medical. This presentation outlines how One Medical's machine learning team has developed an end-to-end pipeline capable of labeling and validating data, running machine learning experiments, and hosting predictive models, all with only 2 configuration files and a minimal amount of code. That's really cool. Enjoy the presentation.
Hi, everyone, and thanks for your time today. My name is Colin. I'm a machine learning engineer at One Medical, and today I'm going to provide an overview of a set of tools that we've developed to streamline the development and deployment of NLP models at One Medical. So before we jump in, just a quick listing of what we'll cover today. First, a brief overview of One Medical for those of you who are unfamiliar. Next, we'll touch lightly on some of the data problems that healthcare is facing. After that, we'll discuss the first component in our model development pipeline, which is data labeling, and we use an open source tool called Doccano for that purpose. Then we'll dive into model development with an internal machine learning tool called OM-ML-NLP. Finally, we'll discuss how One Medical pushes models into production using FastAPI and Terraform. We'll also cover a real-world use case involving social determinants of health, and we'll get more into just what that is in a little while, and of course, questions at the end. All right, so some of you may already be familiar with One Medical, but for those of you who aren't, One Medical is a membership-based primary care practice aiming to use human-centered design and technology to provide quality care that's affordable, accessible, and enjoyable for all. We have over 90 offices across the US and offer 24/7 access to virtual care. Our coverings include mental health coaching, pediatric, and of course, primary care. And we're a vertically integrated healthcare organization. Simply put, our clinical and technology staff and all of our other teams as well work very closely side by side. Along similar lines, we have developed and manage our own in-house EHR system called One Life, which provides a lot of interesting and unique opportunities for data science and machine learning at One Medical. So healthcare is a tricky space to navigate in general, and designing and implementing machine learning powered systems is certainly no exception to this. There are massive quantities of largely unstructured healthcare data locked up in EHRs, medical journals, smart devices, and other sources. One study puts this number at around 2,300 exabytes of data. While a lot of this data is unstructured, structured data is far more valuable. It surfaces key data points used by clinicians to make informed care decisions for their patients. But there's a problem. Providers are squeezed for time and need to summarize patient health while conversing in near real time. And entering rigorously structured data is simply impractical. There's just not enough time, and clicking a box for each and every possible symptom, diagnosis, procedure, etc., just doesn't make sense. The solution is to free up the provider to enter information in a way that suits their workflow and generate the structured data behind the scenes using machine learning. This figure on the right gives an example of how a system like this could be used by a provider scanning through a patient's chart to identify any noteworthy data points. If you imagine that this hypothetical new patient has perhaps dozens of office visit notes like this, comprised largely of free text, plus lab results and other documents, it becomes apparent how much work it actually takes for the provider to get a good sense of this new patient's state of health. Tools like this one can help serve as helpful aids in provider workflows. In this particular example, the algorithm is identifying multiple possible indications of dementia in a single office visit note, something that is likely worth digging deeper into. But do note that this is only a mock-up for demonstration purposes. So how do we get to a place where our EHR is able to do this, able to intelligently extract meaningful clinical concepts out of free text and surface them to our providers? Well, that brings us to the first component of our model development pipeline, data labeling. We need high-quality labeled data sets to train supervised machine learning algorithms. These models that can then take care of detecting and servicing concepts of interest. And that brings us to Doccano, an open source text annotation tool that offers support for text classification, named entity recognition, and sequence-to-sequence labeling, just to name a few. The tool offers a user-friendly, simple interface to label text records, an example of which can be seen on the right-hand side of the screen. Users can highlight any text and then click the appropriate label, for example, occupation or exercise. This data can then be consumed for model development and testing. So since One Medical is a vertically integrated organization, this means that our text annotation platform and our clinical expertise live under the same metaphorical roof. We're able to effectively transfer a portion of their collective clinical expertise into our machine learning models by using Doccano. Now let's take a look at how Doccano can be used as part of a streamlined clinical text annotation process in practice. The first step is creating a new project or a collection of text records in Doccano. We're able to generate a new project by publishing a small JSON configuration file, 10 or so lines. This fires a Lambda function, which pulls relevant data from the desired database, filters and preprocesses the text as needed, and then creates the project and adds the requested annotators. The annotators are then able to authenticate onto the platform, which runs on AWS ECS, and start labeling the data. The data is stored on S3 and is routinely analyzed for quality. Think of things like Fleece Kappa, Krippendorf's alpha, label and annotator correlations, things along those lines. We also have a standardized onboarding process with video tutorials, Q&A sessions, and dedicated Slack channels. And at least one domain expert is assigned to each new use case. So for example, think a sports medicine doctor for a task involving labeling potential sports-related injuries. This domain expert acts as quality control on other annotators' labels, provides feedback, answers questions, and creates a supposed golden data set that is used for testing our models. Once we have our clean labeled text data, it's time to build some models. The effort involved in building models can range dramatically, from just a few lines of code for a simple scikit-learn classifier to hundreds of lines of code, or even more, for certain deep learning architectures. Through years of designing and launching NLP models into production at One Medical, some common patterns have been identified. Most use cases can either be framed as a text classification problem or a named entity recognition problem. For text classification, think things like classifying inbound documents from specialists or routing patient requests to the most appropriate team, for example, the billing team or the provider team. For named entity recognition, think about extracting BI-RADS results from mammogram documents, identifying indications of dementia within office visit notes, or identifying dietary and exercise habits in office visit notes. In addition, some generally performant model architectures and configurations have been identified. And this has all driven the development of an in-house Python library backed by TensorFlow to speed up and standardize model experimentation. This tool is flexible, but has intelligently set defaults based on years of experience training and tuning clinical NLP models, such that the tool has a shallow learning curve and high usability. The tool contains APIs with high-level abstractions for both training and inference. And in just 3 lines of code, you can build, train, validate, and save a model. And production-ready model artifacts can be generated with a simple small configuration file. This tool builds on top of Doccano and facilitates streamlined productionization of models due to the standardization of model artifacts. Here on the right, we can see a simple example of how this tool can be used. We're loading in different types of documents, mammograms, colonoscopies, and colposcopy documents in this case. And with a small config and about 3 lines of code, we're able to train and validate a document type classification model and produce standardized model artifacts. Here's a slightly more in-depth diagram of how we integrate the machine learning library into our NLP workflow using AWS SageMaker. SageMaker is a set of machine learning tools and services hosted by Amazon. So first, as a one-off, meaning that this is only done perhaps one time per major release of our NLP library, certainly not for each individual use case. A general purpose Docker file, about 10 to 20 lines of code, wraps OM-ML-NLP, our NLP library, and generates a model training image which is stored in AWS ECR, their Elastic Container Repository. You can see on the left-hand side of the screen just how simple this Docker file is. It simply installs dependencies, copies the source code, and sets the SageMaker training Python module, and it's that easy. A JSON config file specifying, at a minimum, the training data path, metadata for the training data, so things like important column names, the desired model type, and optionally any model hyperparameters of interest is also specified. This can be viewed on the right-hand side of the screen. In this case, we're training an LSTM classifier on inbound lab results data to detect BIRADS codes, which are a standardized mammogram result code. We also specify the fraction of data we wish to allocate to training and specify a few model parameters, such as the desired embedding and vocabulary size as well. The user can then make a call to AWS SageMaker in whatever language they prefer, pass the config parameters in, and wait until their model artifacts and performance metrics are ready for review. By integrating this tool into AWS SageMaker, we're able to effectively abstract away the environment, the compute, and even the language, and we free up our machines and our minds for other work. This is also a very safe and compliant way of training and analyzing clinical models, as the data never actually leaves the cloud. All right, so far we've covered labeling data and training and validating models. So the final step is taking those model files or artifacts and putting them to work in a production environment. That's easier said than done. Productionizing models is notoriously difficult, frequently involving a high friction handoff between a model development and production engineering. However, having a reliable standardized set of model artifacts is conducive to a simplified productionization process. And we do this using FastAPI and Terraform. So FastAPI is a Python web framework for building APIs. It's considerably faster than Flask. It offers asynchronous support, which is very useful for side effects like logging model predictions to a table. It also automatically renders API docs via OpenAPI and JSON schema. We've abstracted all the core functionality of a general inference task into a FastAPI-based Docker image, which can then be utilized as a parent image for each individual use case or project. The developer simply needs to define a standard predictor Python module that conforms to some simple guidelines, and we're almost ready to go into production. The other piece of the puzzle is the infrastructure needed to host this inference service. And for this purpose, we leverage an infrastructure as code tool called Terraform. We host our services largely on Amazon ECS, which stands for Elastic Container Service. In very simple terms, you specify a Docker image and ECS runs it. We've developed an in-house ECS microservices Terraform module, which allows for essentially plug-and-play implementation of new inference services. You just pass in your inference Docker image path that's in ECR, plus some other key properties, and you let Terraform do its thing. Within a matter of minutes, you're up and running with a brand new inference service. And this is really nice because it abstracts away all the messy networking, permissions, etc. infrastructure work that goes into launching a secure new service. Let's look at an example here to get a realistic idea of just how much work goes into taking the model artifacts and creating an inference service. On the left, we define our predictor class, inheriting from the FastAPI base predictor class. This class is the only Python code we need to write for our inference service. It's instantiated by the parent FastAPI Docker image, and all the logic around this predictor class is effectively abstracted away. You'll also notice that this class leverages the NLP library's inference methods, load model and predict. These are common methods regardless of model type. On the right, we have an example of our Terraform ECS microservices code. Note that only 8 input arguments, at a minimum, are required to build out all the infrastructure for our inference service. You can specify things like the CPU, memory, and desired task count to make sure that your service can scale to fit its needs. And here at the bottom, we can see a mock-up of an API call to the service in the inference services response. Hopefully this demonstrates how worthwhile it is to invest effort into a standardized model productionization pipeline, especially if your team is rolling out new models at a relatively high rate. The return on investment is tremendous. And now, putting everything together, a real-world example of how these tools have been used at One Medical to quickly build and productionize a deep learning model to detect social determinants of health. What are social determinants of health? They're social and economic factors, such as your diet and exercise habits, relationship status, and alcohol consumption, just to name a few. And they play a critical role in determining patient health outcomes. Having structured representation for these data points allows us to provide better care coordination and patient outreach. However, our patients and providers don't always have the time to fill out lengthy survey-like questionnaires covering social determinants of health. But we can find this data spread throughout a patient's chart. This is a typical named entity recognition problem, and we use an LSTM-CRF model to tackle this. 7 different determinants were selected for this project. We have relationship status, diet, exercise, alcohol, caffeine, and drug use, and occupation. Just a few numbers here highlighting the work required to build out this model. So in total, for creating the text labeling projects in Doccano, it took 20 lines of JSON config, no Python code or anything like that. For model training, another 20-ish lines in a JSON config file, and less than 10 lines of code in total for SageMaker deployment of the NLP library of the model training job. Finally, for model productionization, we have less than 100 lines of code spread between the required Python predictor module, the application-specific Docker file, and the Terraform config that we saw examples of on the previous slide. All of this, including time spent labeling data, took just under 4 days. You can take a look at the model accuracy on a per label basis in the table on the right. It's 90+% accuracy across all but one label. So with relationship status, we have 87% accuracy, diet 97%, exercise 99%, alcohol 94%, caffeine 91%, drug use 92%, and occupation 96%. So pretty good performance, and it really didn't take a lot of time or coding effort to get to a place where we have a deep learning social determinants of health model ready to run in production. So that's it. Thanks for your time, everyone, and we can take questions.
That was Colin, Waldman, Senior Machine Learning Engineer at One Medical, outlining how One Medical's machine learning team has developed an end-to-end pipeline capable of labeling and validating data, running machine learning experiments, and hosting predictive models with only 2 configuration files and a very minimum amount of code. If you enjoyed this presentation, if you'd like to watch more videos like this, you can subscribe to the DSS Insider program, where you can see our complete on-demand video repository and watch it whenever you like. And also don't forget to subscribe to our channel below. Thanks!